Alright, so last time we defined some terms and concepts, so now we're going to talk about the nitty-gritty of how you convert between marginal probabilities, joint probabilities, and conditional probabilities using a contingency table. So here's what one looks like. And the idea is you have a list of possibilities in the row. So this is a set of events over here in the rows, and you have a set of events in the columns. So this would be, you can think about A's and B's from before, A being the rows and B being the columns. So my A event, what's my probability that I buy a TV or that I don't? Right, so A can be TV or A can be not, B can be DVR yes or DVR no, and so over here I've got 300 people that have come through the doors of my store, and 38 of those people bought both, 42 just bought the TV, 70 just bought the DVR, and 150 didn't buy either one. So in total, 108 people bought DVRs, 80 people bought plasmas, and 220 people did not buy TVs, and 192 people did not buy DVRs. So I've got row totals, column totals, and then a total down in the corner. So I can think about a couple different things I can do with this. So in terms of marginal probabilities, what's the probability that I buy a plasma screen? Well, 80 people buy a plasma, and 300 people go through the door. So it will be 80 divided by 300. That's a marginal probability. What about a joint probability? What's the chance that I buy both a plasma and a DVR? Well, 38 out of 300 would be that probability. These are objective probabilities. We have a total number of trials and a number of occurrences here. Now, conditional probabilities get interesting. But we can read them right off the table, and it shows, writing it this way is pretty, I guess, educational, and that you can see where they come from. So let's start with the conditional probability that says, well, what's the chance that I buy a plasma screen, what's the chance that I buy a DVR given that I buy a plasma screen? So remember, well, let's just look just in general real quick. What's the chance I just buy a DVR? So I just buy a DVR. It's 108 out of 300. So it's basically 1/3. Okay, that would be our marginal probability. Now, if I've just bought a TV, am I more likely to buy a DVR or less likely? I would say probably more likely. I mean, certainly, maybe you have a budgetary constraint or something, and you've used up your money and now you can't. But often, once you've got a TV, you may want to do something. You may want to have a DVR unit to use to augment your newly purchased TV. So we can test whether that assertion is true using a conditional probability. So if we're right, then the probability of getting a DVR is higher once you've bought a TV. So what we're interested in is probability of DVR given TV. So in order to do that, we need to focus on the plasma yes row. So if you think about it, 80 people bought a TV. Of those 80, 38 bought a DVR. So the chance that I buy a DVR, given I've already bought a TV, is simple to see from here. It's 38 people out of 80 people, or roughly 1/2. So it's 1/3-ish when we are not purchasing a TV, or just in general, whether we bought a TV or not. But if we focus on the TV sample, we get about 1/2. That also means we can think about what's the chance that we buy a DVR if we didn't buy a TV. And notice that's 70 out of 220, so that's slightly less than a third instead of slightly more than a third. So you're less likely to buy a DVR if you don't buy a television. So, our idea turned out to be right, and we can calculate those probabilities using this contingency table. So here this is in math. You're just adding up. You either use the totals or you don't, depending on the kind of probability you're calculating. So now let's think about a problem we can use this idea for. So suppose Mars hopes to introduce a Snickers energy bar, and they think that they have a 50% chance of success, and they make 300 million if it is, and lose 800 million if it's not. Obviously, 50% chance of success is not good enough. So we need to know. We need more information. We need to either need to know for sure that it's going to be a failure, or know for sure that it's going to be a success, or at least know with more accuracy. So one thing that's often done is to conduct a focus group study. And maybe we've got experience with doing focus groups, so we know that if I have a successful focus group, then I'm ultimately successful. We often talk about this in terms of biomedical. So this is like if you've got a medical test, how often do you detect the disease and how often do you return a false positive? So in this case, we're saying of the products that ultimately were successful, 80% had good focus group studies. So if you can just imagine, we've got a history of introducing new products, and we had 100 new products that we introduced. 80 of those 100 new products would have had successful test markets. And let's imagine that we had 100 products that failed. 30 of those failures had successful test markets as well. So the probability of the focus group liking the product given that it's successful is high, and the probability of the focus group liking the product given that it's bad is low, but it's not perfect. So the question is, if we can do one of these, how much more likely is success if we get a good result? So if the focus group likes it, certainly it's not 50, it's not 100 either, but what is it? And so that's where a contingency table and a conditional probability becomes really important. So this is the general recipe that we'll do to solve this. So in the given information, you're going to have at least one marginal probability in general. So in our case, that was, which was the marginal? This one right here, 50%. So we have a 50% chance of success. That's the probability of success of 50%. That's a marginal probability. It's not joint, it's not conditional. Okay. So we're going to create a contingency table. And so the big trick, notice here, we don't know how many observations